So in the last video, you saw what is electrostatic potential energy. The potential energy that's stored in a spring system, and we saw it is equal to half kx squared. In this video, we're going to look at two further concepts. We're going to explore further two concepts of electrostatic potential energy. Now, this has a lot of application. One simple application I will tell you, which Robert Hooke himself invented, what is known as the balance watch. Now, we know that the watch, a needle keeps ticking, and many of you may have seen where a watch where you key the spring, you key the watch, and then the needle runs. Well, that is based actually on the spring technology or the electrostatic. I always keep mixing that up. Elastic potential energy idea, where you key a spring, elastic potential energy is stored, and this elastic potential energy then gets slowly converted to kinetic energy, and the needle keeps going round. Well, that was an invention of Robert Hooke. But in this particular video, we're going to look at two concepts. Okay, the first one, now, as I said, there is a spring and it is in its equilibrium position. It is attached to a body. Equilibrium position means there is neither stretching nor compression, so that's x is equal to 0. Now, I start stretching the spring towards the right, and we know that force starts as the spring force will come into action, and the force is acting to the right. Similarly, if I compress it, you will see the force starts acting in the opposite direction towards the right hand side. The force comes into play, and that's how it works. Now, if I were to plot this force versus the displacement from the equilibrium position on a graph, now this is what this graph is. It plots the force against the displacement from equilibrium position. The plot would be a straight line, and this represents the line f is equal to minus kx. We already saw it in the last video, f is equal to minus kx. This is how the line is. Now, graphically, we're graphically solving this problem of elastic potential energy. So at any point, let's say x, suppose I want to find at a displacement x, the spring is displaced x, I want to understand what is the elastic potential energy. How do I find it? It's simple. It's the area under the graph, right? I plotted the line. I just need to find the area under the graph. There is this area of this triangle would be the elastic potential energy. And we know that the area under the triangle, this is kx, this is x, it will be half kx squared. And we've already derived it using the work integral f dot dx. We saw it equal half kx squared. Even graphically, you will find that the answer is half kx squared. Similarly, if you pull the displacement in the opposite direction, the idea remains the same. The area under the graph will give you the the elastic potential energy. Okay, so that's the first idea I wanted to discuss with you. I come to the second and more interesting idea. We already saw that this force, spring force, is a conservative force, right? And therefore, conservation of mechanical energy applies to the spring system, right? And how does it? And we can see it in work. And in fact, most of the applications of the spring are based on the conservation of mechanical energy, or the conservation of energy, which is the broad principle of energy, conservation of energy. And let's see how it is applied, how we can apply conservation of mechanical energy to the spring system. Now, the body is in equilibrium position. I stretch the spring by x, right? And I leave it. I'm sure a lot of you have played with you. What do you think happens? Have you seen what happens? Yes, the body will come to the equilibrium position with a certain speed, and then it will overshoot this position, come to the left side, and then go back, and then suddenly there's an oscillation. There's a to and fro motion and an oscillation which is taking place, right? Now, what is happening here is that when I pull the spring to its maximum, let's say a position displacement xm, and I hold it there, the system now has elastic potential. When I leave it and the body starts moving, this potential energy is getting converted to kinetic energy, right? And it comes to the equilibrium position. At equilibrium position, we know potential energy is equal to 0 because x is equal to 0. That means all the potential energy is converted to kinetic energy. But then it overshoots this position, and you'll see that the body now slows down, and it comes to, on the left side, the maximum displacement you will see will be minus xm. It will overshoot, come to a position of displacement minus xm, where it stops, and then it goes back. And this oscillation will continue. And at this position minus xm, all that kinetic energy will get converted once again into potential energy. So in this to and fro motion, you see potential energy getting converted, kinetic energy getting converted, potential energy back, and this system goes uh, to and fro, and you see the conservation of mechanical energy in front of your eyes, right? It's a beautiful system which explains this concept. Um, a few math, to get an idea, like let's extend it to a maximum displacement x and leave it. What would be the speed or the velocity of the body at its equilibrium position, right? Now, when I stretch it to its maximum position at, let's say, at maximum displacement, we can see that the potential energy is half a xm squared, right? And when it reaches its equilibrium position, you'll see the potential energy is zero and it has only kinetic energy. So I can say half mv squared, right? So because all the potential energy gets converted to mechanical energy, gets converted to kinetic energy. So you can say the v over here, my 2 gets cancelled, will be equal to root of k by m xm, right? This will be the velocity at equilibrium position, and this is also the maximum velocity that the body can acquire. Okay, so the velocity can either be in this direction or that direction based on which it is moving, it is oscillating, right? I can also look at an intermediate position and solve for it, and let's say at any position, I'm going to take this side for a change, let's say x, right? I want to understand what is the potential, what is the speed, what is the velocity of the body. So once again, my conservation of mechanical energy applies. At the initial stage, my energy is half k xm squared. This is the maximum energy that the body can have. This is equal to half kx squared. So the body is at a position, any intermediate position x, the potential energy will be half kx squared, and your kinetic energy will be half mv squared. And I can solve for v over here. You can say v is equal to my 2 goes, and I have root k by m xm squared. This value comes this side minus x squared. So at any intermediate position x, this would be my velocity, right? So you'll see, and how do you represent this graphically? This graph, it's a very elegant way of representing it. It's a very beautiful way of understanding this concept. This graph represents how the energy, the total energy is given by this line, right? The line over here. How this energy is oscillating between potential energy and kinetic energy. So let's say at zero position, you see that potential. This line represents potential energy, and this line represents kinetic energy, right? So at the other way around. This is kinetic energy, and this is potential energy. So at maximum displacement, you can see that the potential energy is maximum and kinetic energy is zero. And as the body starts moving towards equilibrium position, kinetic energy becomes maximum, potential energy becomes zero. When the body overshoots and goes to maximum displacement towards the left, given by minus xm, where again potential energy gets maximum, kinetic energy gets minimum. And this graph shows how to and fro the potential energy gets, the mechanical energy oscillates between potential energy and kinetic energy. But at any point of time, the sum of kinetic and potential energy should be equal to that straight line, which is equal to the total mechanical energy, which proves the conservation of mechanical energy. Okay, so here brings this video to an end.